Hey guys, this is Brandon's project right here. Today we'll start with chapter 3, section 4 on velocity and rates of change. So let's get to it. In this section we examine some application in which derivatives as functions are used to represent the rates at change which things change in the world around us. It is natural to think of the change as change with respect to time, but other variables can be treated in the same way. So this is the difference quotient right here, and if we interpret the difference quotient as the average rate of change of the function f over the interval form x to x plus h, we can interpret its limit as h approaches 0 to be the rate of change which f is changing to the point x. So what this means is the instantaneous rate of change of f with respect to x at a is the derivative. So f prime of a is equal to the limit as h approaches 0, f of a plus h subtracted by f of a over h. So I know this seems a bit long and frustrating, but this is actually really simple to use. So if we go to our next page, so f prime of a is equal to the limit of h approaching a, f of a plus h subtracted by f of a over h is basically the same as the rate of change, which is also the same as the instantaneous rate of change, which is practically the same if you see those two, but is also equal to the slope of the tangent, which is also equal to the derivative. So it's at key, it's equal to derivative. Now we go back, which is basically equal to f prime of a. So f prime of a is basically equal to derivative, which makes things a whole much simpler if you just break it down like that. Rather than just using the f prime of a is equal to a limit as h approaches 0, f of a plus blah 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 blah, we're going to skip into our example and just find the derivative of what it's asking. So example 1 is enlarging circles. We go to our first step A. Find the rate of change of the area A of a circle with respect to its radius r. So again, the rate of change, which is equal to instantaneous rate of change or derivative, we're going to take dA over dr is equal to ddr of pi r squared. When we get that, we use the power rule to bring 2r multiplied by pi, which your answer is going to be 2 pi r. So it seems a whole lot simpler when you're just rather using the derivative or finding the derivative rather than just using this in being intimidated by this formula right here. So now moving on that we found our rate of change, we go to our next step in the example. Part B. At r equals 5 and r equals 10, evaluate the rate of change of A. So basically what we need to do for this question is that we just need to plug in r, what's being asked. So r equals 5 and r equals 10. We have 2 pi of r. So we have 2 pi, input 5 as r, and you'll get 10 pi, which is probably 31.4 based on pi being 3.14. And then we have 2 pi multiplied by 10, which is equal to 20 pi. I'm too lazy to do that math, so we're just going to move on. Now part C. Part C, if r is measured in inches and a is measured in square inches, what units would be appropriate for a dA dr? So, since we have dA dr, we have a as being n squared inches and dr being in inches itself, so we're going to have square inches per inch. Example 1 covers rate of change and all right now, so we're going to move on to velocity itself. Getting to there slowly. This motion along. So that covers some form of rate of change. So on to our next part. Motion along a line. Suppose that an object is moving along a coordinate line, say an s-axis, so that we know its position s on that line is a function of time t. So x-axis being our previous line, as in just creates a horizontal line, but now we're switching that to the s-axis. S is equal to the f of t right now. The displacement of the object over the time interval t to t plus delta t, I guess, is that the triangle? I think it's called delta. The displacement of the object over the time interval from t to t plus delta t is delta s equal to f of t plus delta t subtracted by f of t. But then that also leads us to the average velocity. The average velocity of the object over the time interval is v of a displacement over travel time is equal to delta s over delta t, which is equal to f of t plus delta t subtracted by f of t over delta t, which kind of looks familiar as we saw before in the rate of change, which is actually the instantaneous velocity. So again, instantaneous rate of change. Again, it's referring back to derivatives, so it's simple. It's not that hard to connect 1 and 2, which basically equals 1 is equal to 1, which is equal to 1, which is equal to 1, and so on. Besides telling how fast an object is moving, velocity tells the direction of motion. When the object is moving forward, when s is increasing, the velocity is positive. When the object is moving backward, when s is decreasing, the velocity is negative. If we drive to our friend's house and back at 30 miles per hour, the speedometer will show 30 miles on the way over, but will not show negative 30 on the way back. Even though our distance from home is decreasing, the speedometer will always show speed, which is the absolute value of velocity. Speed measures the rate of motion regardless of direction. So, speed is also absolute value of velocity. Speed equals absolute power of v of t, and is equal to absolute value of ds over dt, which gives us to our next topic, acceleration. The rate at which a body's velocity changes is called the body's acceleration. The acceleration measures how quickly the body picks up or loses speed. Acceleration is the derivative of the velocity with respect to time. If a body's velocity at time t is v of t is equal to ds of dt, then the body's accelerations at time t is a of t is equal to dv over t is equal to d2s over d2 t2, my bad. So just in other words, the acceleration is actually a derivative of the velocity. So in short terms, the acceleration is basically just the derivative of the velocity.
Alright, and on to example number 2, modeling vertical motion. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160 t subtracted by 16 t squared feet after t seconds. Part A. How high does the rock go? So the first part in solving A is to find the instant when the velocity is 0. So we're going to have to find the velocity and make it equal to 0. So we have v is equal to ds dt of 160t subtracted by t squared equals 160 subtracted by 32t feet squared. 160 subtracted by 32t is equal to 0, so we have to find t, and if we just plug in 5, then it's going to be 160 subtracted by 160. So now that we have the time that velocity is 0, we're just going to plug in 5 into the old equation. So we have 160 multiplied by 5 subtracted by 16, 5 squared is equal to 400 feet. Part B. What is the velocity and speed for the rock when it is 256 feet above the ground on the way up and on the way down? To solve this, we need to find the zeros of s of t. So it'll be s of t is equal to 160t subtracted by 16t squared is equal to 256. Then we must move the 256 to the left side. So just check that over. So then it'd be 16 squared subtracted by 160t plus 256. Once we have that, since it's asking for the velocity and the speed, we just plug in 2 and 8 into the velocity. So it'd be 160 subtracted by 32t is equal to 96 feet per second. Next we plug in 8, which is v of 8 is equal to 160 subtracted by 32 multiplied by 8, which is negative 96. And of course, the speed is the absolute value, so what we need to do is just put the absolute value in there, and then you have that 96 feet per second is your answer. What is the acceleration of the rock at any time t during its flight? So, to find the acceleration, it's a is equal to dv at dt, which is the derivative of the velocity. And we find that it equals 160 subtracted by 32t, which is equal to negative 32 feet seconds cubed, I believe. So in this part, the acceleration can be negative, unlike the speed. So that's what we're gonna have. And finally, part D. When does the rock hit the ground? So for this, we're going to have to find the zeros of the function s. Unlike the other question, we don't have to use 256 because that information wasn't given to us. And it was just 256 above the ground. So it didn't exactly have a time in this, but we're just using the final seconds on which the rock hits the ground. So we have s is equal to 160t subtracted by 16t squared, which equals 0. Now to find the zeros of that, it's kind of simple. We just plug in 0 right now, so that's going to be 160 subtracted by 16 squared, which if you just multiply that out, it's going to be 0. But this is going to be the time the rock starts and goes off the ground, so this is the initial time of departure. Moving on, if we also just plug in 10, then it would be 160 multiplied by 10 subtracted by 16 10 squared, which is 1600 subtracted by 1600, which equals 0. So this is the time ended now. That has come down. So now that we have the time that it has ended and hit the ground, then our answer is 10 seconds. So that's going to be the end of 3.4. Not too much. Things to highlight is that instantaneous rate of change means rate of change, which is equal to the derivative, or f prime of a, or whatever. Remember that s of t is the. No. Remember. Oh my God, this is a cat. What? I don't have a cat. What? August, there's a cat. August. There's a cat. There's a cat. So remember that the acceleration is the derivative of the velocity, and the velocity is actually the derivative of s as in x. So that's it. Just apart from that, and finding the derivative and possibly finding the zeros of the velocity or the acceleration or of s, which gets you a lot of answers. Thank you for watching, and I hope this went wonderful.